Hello, and thanks for watching Rust in 15 minutes. Of course, to spice it up a little, I put it all in relation to Go. So here and there will be a, well, hopefully truthful comparison to Go, and all of those of you who know Go can kind of relate to Rust a bit better, I hope. So this is why I did this in the first place. Also, it's just 15 minutes, and 15 minutes is not really enough to, well, go deep on anything really. And probably many questions that you have will be left in the open, and answers are out there though, because my talk is based on another one called Intro to the Rust Programming Language by Alex Crichton. Sorry, I should probably prepare better and know that. Or know how to pronounce that name. So it's 45 minutes of awesome, because this guy is truly great, knows his thing, knows it much better than I do, just saying. I just give a little overview. This is much closer to what you can expect then. But I try to focus on what really matters. All right, so what is this fancy new thing? Rust, ta-da! Rust, according to rustlang.org. Let me read it out loud for you. Rust is a systems programming language that runs blazingly fast, prevents almost all crashes, asterisk, and eliminates data races. In theory, Rust is just a work in progress and may do anything it likes, up to and including eating your laundry. Yes. We'll get to that in a quick moment, but let's have a real quick look at what we see here. Featuring zero-cost abstraction, smooth semantics, guaranteed memory safety, threads without data races, yada yada yada. Trait-based generics, maybe that I wanna say out loud here as well. Yeah, that's pretty nice, but you know, I think the most important thing here is, at first, Rust is still alpha. I mean, sure, it's clear from the landing page of rustlang.org, but let me say it again. Rust is still alpha. But fortunately, by now, we have an actual timeline. So the first beta is due to arrive on the 31st of March this year, and version 1 will be there on 15th of May this year. So just be ready. I mean, you know, alpha is something you might just not want to be up to, but the beta is something I want to motivate you to have a look at. This is why I do this. I want you to know that you should look at this once it's better, at least. Rust, you know, Rust is, if you want to put it onto a line, comparing it to other current time languages, you know, it's not really on it, because Rust is safe and fast. If you look on the C++ side there, you have lots of control about the memory layout and memory consumptions of your program, but all this is relatively unsafe, because getting a sec fault, crashing your program, having weird heartbleed-ish bugs there is very, very easy, but you get high performance, super high speed. Then somewhere in the middle you have Java, which is, you know, has its advantages and disadvantages, quite impossible to get sec faults there, and on the far right, you know, Python or Ruby, which are super slow, but you know, it's still impossible to kind of hard crash your program. Rust, on the other hand, is kind of, yeah, there. It gives you all the control you ever wanted about your memory layout, to the point where it gets unsafe. So Rust is safe, therefore you have a lot of control, but certainly not all the low-level memory stuff that you would usually do in C, at least not in safe code. It ends up, even though it's safe and has lots of constructs that make your code safe, it ends up being as fast, well, or at least competitively fast with C and C++. It's super fast, honestly. And that's already the case, even though it's alpha. Rust is safe, and they say this, you know, that's the first thing you read. Rust is safe everywhere, because that's one of the main ideas of that language. It's supposed to be safe by default. And that should be said as well. So of course it's possible to write unsafe code, and considering it easily operates with C code, there is code that can be unsafe. But all that code is specified or marked as such. Therefore, it's not a real problem, because at some point the programmer is just saying, yes, my dear compiler, I'm telling you this is safe, trust me. And you put it into an unsafe clause, and that's how that works. But the main reason why Rust is safe is its super sophisticated type system. which allows the compiler to do an analysis that you have never seen before. At least I haven't ever seen something like that before. This analysis allows you to track ownership. Okay, here we have a simple program. And that's actually a working program, by the way. You can compile that and it will run as a standalone binary. Let's see what we have here. What we do is we create a number 5 on the heap, which is this box new construct here. And then we pass it on to a helper function. And right after that, we try to print it out. That's kind of the standard print line that goes to standard output. The helper function takes a value of type box u32, which also just tries to print this value. So far, so good. But what would actually happen, or what actually happens here when you try to compile it, is this error, use of moved value slot. And then you have some stuff that you probably skip over at first. Okay, expansion side, macros, I didn't know I use a macro there. Last line there, slot moved here because it has type box u32, which is copyable. So slot moved here. That's the move semantics mentioned on the landing page. And in the moment, something moves somewhere else, ownership is transferred. So initially, the slot variable here owns that newly created box value. And in the moment you hand it over to that helper function, it's not, just going there, it's moved there. So all of a sudden, the helper function owns that value, which also means that no one else may now use the variable or the item in any way. Of course, you could say, well, that's all very nice and such, but I can't imagine writing any program like this. And that is true, because if things can only be owned by at most one entity or one thing at a time, then yeah, you're kind of limited. And this is where borrowing comes into play. Again, this is a, theoretically fully working program. And borrowing is all happening here. The ampersand here is the borrowing operator. It's the address of operator in many other languages, and it can behave like that, but in Rust you should really think of it as a borrow operator. What happens here is that we create a new vector that contains just one entry, which is the string hi. And what I do here is I borrow the first value, I borrow the hi here and put it into a variable hi. And what I try then is to change that vector by pushing ho onto it, and then I just print my hi. So let's see what Rust has to say about that. Error. Cannot borrow v as mutable because it is also borrowed as immutable. Honestly, let's try to figure out what that means. Note. Okay, notes are always helpful. Previous borrow of v occurs here. The immutable borrow prevents subsequent moves or mutable borrows of v until the borrow ends. So here, the immutable... How did that happen? All right, let's try that again. I'm sorry. So this is why I do this, just to figure out what can happen, what can go wrong. So again, here we have the borrow, here we have the error, and as you can see, what happens is that I have an immutable borrow right here, and then I try to mutate something that has implicitly be borrowed. I mean, I have a borrow to v, because I'm borrowing part of it, right? So borrowing as ownership tracking is a deep thing. It goes deeply into your structures or types. In the moment you have an immutable borrow somewhere, you're not allowed to mutate the original value anymore until the borrow ends. This prevents data races, because if someone can write while someone else can read, possibly, theoretically, even though I'm not doing this here in the code, but if it can be, then it's forbidden. And this is how this compiler works. So if we want to make this work, we just have to swap line 3 and line 4 so that we first do the mutation and then we take the borrow. And this will work just fine. Something you kind of see here is another great feature that leads to Rust's great safety, which is immutability. I call it immutability because in Rust, things are actually immutable by default. You cannot change a thing unless you explicitly say that you want to change it. This is new. I haven't seen this anywhere before, but maybe it has been there. I by no means know all the computer programming languages out there. How could I? It's like a terzillion by now. But yeah, let's see what happens with this code. Maybe I should talk you through first. So we create a simple 1 that we bind to the variable v here. And then we try to pass it on to the add1 function, which adds 1. And then we just verify that it is now 2. Add1 is defined to take a mutable borrow of a U32 integer, unsigned with 32 bits, by the way. And then we just dereference this guy and add 1 to it. That's what we do. So that looks pretty good to me, but let's see how it looks to the compiler. Error, mismatched types. Mutable borrow to U32 was expected, but he found a borrow, which is by default immutable, of a U32. So it just tells you, in case it's not clear, values differ in mutability. And this is where it happens. Here, right there. And the problem here is that we didn't specify that we want to borrow v as mutable. And this is what we are doing right now. As you see, and that's an awesome feature, just to make the code more explicit. In the signature of the function, we specify that we want to mutate, that we want to change the borrow that we take here. That's all right. But in Rust, you also have to say so on the caller side. So when calling a function, it always is clear what's going to happen there. Either you borrow a value or you borrow a mutable value, but it will always be written when calling the function. You could say, yeah, I have to write more now, yeah, but that's a trade-off for being so explicit about it, which makes your code more maintainable. So in theory, this will work. But in practice, it tells you, error, cannot borrow a mutable local variable v as mutable. So it claims that this local variable is immutable. And you know, if anybody of the compiler programmers of Rust reads this, I would be glad if you could kind of add the line where v has been defined as immutable in this case. So here you go. You see it? Let v be a 1. But as I told you, everything in Rust is immutable by default. So in order to allow us to mutate, to change that value, we have to write it like this. Let mut v be 1. And now, from a mutable v that I own in the first place, I can give out mutable borrows, which will now make the program work just fine. Of course, safety is one thing, and you know, if I want to have a safe program that runs like 10 times slower than C or 10 times slower than Python, then I would not use it. Because I can't have it if my CPU is burning for nothing, wasting energy, wasting time. I mean, you know, we can't afford this really. Earth is heating up, right? So Rust is also efficient. Rust is fast. Rust doesn't have garbage collection, so you will deal with memory more or less, well, implicitly through smart pointers. There are lots of types of smart pointers. There's just a simple auto pointer, and there are reference counting pointers and things like that. This means that you can, in fact, you know, garbage collection is not always a bad thing. This means that you can, in fact, run into memory leaks in the moment you have cyclic references of items to each other using reference count as pointers, so the count will never be 0, so things will never be allocated. That's something you can always run into in such a system. Weak pointers are available, though, just saying. So now that I kind of said I'm going to compare things to Go sometimes, here we go. So Go has a garbage collection, and Go's garbage collection is pretty awesome, in the sense that you cannot ever have cyclic references hanging around, because it's not, you know, it's tracing the references actually and has a look at them actually without relying on a particular count. What else is there that makes Rust efficient? Rust has generics. Generics, templates, however you want to call it. Of course, it's better to call it generics because templates are kind of a C++ term. This means that most of the time you actually rely on generics, which boils down to code which is working exactly on the type you throw in. That means no virtual function call overhead at runtime, because it's all resolved at compile time. Concurrency primitives are there too, because nowadays if you can just run on a single core, you wouldn't really help much in terms of efficiency, and a modern language has to make that rather easy. Of course, Rust can do that too, but as you will see later, there's much less syntactic sugar around it compared to Go. Of course, last but not least, we produce small runtimes or small binary files that are completely statically linked. So whatever you have there, it will just work out of the box. Even the runtime is linked in there, so it is as small as it gets. And that's totally awesome. I will show you more about that in a moment. Let's have a look at generics. Okay, this is quite a massive program, and honestly, if you don't understand anything here, it doesn't matter, because you don't have to. What we want to focus on is just the main bits here. What do we have? We have a chihuahua, which is an unsized item. Yeah, chihuahuas are quite small, so here we don't even have a sized. It's an unsized struct that we assign to he, and we have a bulldog, I suppose, that is something instantiated from any dog that can make any sound, basically. And we let them fight against each other using a monomorphic implementation, that one here, and a polymorphic implementation. As you can see on the caller side, it looks pretty much the same. We just hand out borrows to our respective dogs, and off it goes. But here, on the definition, it looks a bit different. The monomorphic version, the one that uses generics, says, okay, we have two types here, and both should support the barker trait. So barkers, as you can see here, barkers can bark, and they do that on an immutable borrow. So this means that basically they won't change themselves while barking, which makes sense because, just returning a static string here. And with that in place, I can just bark as much as I want. That's fine. The cool thing is whenever I call this one, it will resolve to calling exactly the right bark method on my input value. It will compile down to whatever is needed depending on the types given. This also means that more code is generated, which can make your executable larger. This thing will basically make your executable faster, but also potentially larger. Potentially, that always depends on your particular case. The polymorphic version is a bit easier on the eyes, a bit easier to read, because all you have to say is that you want items here, borrows, that support the barker trait, and that's it. And then you can just bark ahead, but this will be resolved at runtime. So in Rust, you have the choice of what you want to do. And if you look at the Rust standard library, you will see that most, if not all of it, is solved using generics. This makes everything rather efficient and fast. And that's also something I totally love about Rust. Good, workable, usable generics, as opposed to, for instance, C++, where templates are kind of an advanced thing. And compared to C++, not to forget, what bothers people about C++ templates usually is that they will give you all sorts of weird errors that you don't understand when you try to use them. Whereas Rust will give the one implementing the template or the generic all kinds of errors, because it does check the template at compile time, not at instantiation time. That kind of moves errors to the implementer and not to the user of the template or of the generic. And that's totally awesome. That's what you want. Then, how would we write a concurrent program in Rust? Well, I will spare you some details, but I've chosen this example here because all the Gophers among you will kind of possibly be able to make sense of it. And one thing is obvious. Rust is much more verbose about things because it has actually no syntactic sugar to do things like channels and to do things like spawning threads. So as you can see, you use native threads here. You don't have Go routines or anything like that. And in order to spawn, you do it like this. You don't have a keyword to like Go to spawn a new function and execute it asynchronously. This is how that works here. But let's start at the beginning, right? So we have a channel that is used to deliver input, the work that is supposed to be done, and an output channel that is containing the values that have been produced by the worker thread. Each channel consists of two ends. So we have a read end and a write end, or a sender and a receiver here. The TX is the sender, the RX is the receiver end. And we can now basically pass along these ends as we like. The first thread here is consuming work. So we have a little closure here that will just iterate the input channel to get some numbers out of there, and then he is sending the result, which is just the number multiplied by 2, to the output channel. Also, something you can see is that, that's something else that is kind of implied that I've never really talked about, is the way Rust handles errors. And error handling is a big thing for safety, if you think about it, because if you never handle errors, then at some point your program will crash at a, well, maybe unrelated position in code. But whenever there is something that can go wrong in Rust, you will have to deal with it in some way. The compiler will even tell you that you are ignoring a return value that must not be ignored, that must be used. So what I'm doing here is I'm saying, okay, I trust this thing. I'm just unwrapping the result, and if there is an error in there, my program will abort. At least the thread here will abort with a panic stating the reason that is contained in the result structure that I get here. And all this just by sending to a channel, right? But this channel could be closed at some point. This channel could be broken. So yes, we have to check our results. The great thing is that my sending end here that takes the output values is dropped here, because actually all the values that we see here, they are moved into the thread, which means the thread takes ownership of everything it touches. This means there's no overlap in basically data, which also prevents data races quite effectively if you think about that. So now that OTX is owned by the thread, once we reach this, once our loop breaks here, we drop our OTX, which also allows our aggregator to stop looping, which comes later. So here's the thread that does the work part. Same thing here, we spawn a new thread and move all the stuff in there. Here we just loop. And that's kind of the short version to write, yes, we want to loop in the range of 1 to 4. That's an exclusive range here. And all we do is we send these values along the input channel. And here you see another way to handle errors. Just for completeness, what we do is basically discard all the errors. And I expect this value still to have worked out fine for us. So if I expect a positive value to be in here, otherwise we will still panic, but with a different error message this time. We will panic with send work, failed, something like that. So again, IDX is dropped here, which I cannot spell, breaks the consumer's loop. So in the moment this guy is done producing his values, this guy, which reads on IRX, can also stop looping, and then this is how all my threads will implicitly, or kind of implicitly know when to stop and when to go down. Last but not least, in the main thread, we are aggregating the results. I'm just putting this into a vector, and again, at some point I had more values here, so I'm just explicitly instantiating a vector with a capacity of 10 items. 10 items because I don't specify types here. As you can see, it's all inferred. The type inference is quite amazing. If you think about it, where do I name any types here? Not in too many places. And I just collect the results, push them onto my vector just to make an assertion here. And it's really difficult for me to point down there. But right there, I just verify that the values are all coming the way I expect them and in order. So the same example in Rust would look, in Rust and Go would look quite different, I suppose. Less code, but yeah, I like I like the way I can drop the handles here, which automatically makes loops end on the other side. I really like the explicitness. Oh, well, explicitness. I really like how this works. Last but not least, the runtime, right? If it produces runtimes of 10 megabyte, then this kind of makes sure that you will have trouble running on small devices like little Internet of Things devices that don't have much of anything really. So Rust is a systems programming language in the first place, so it must be possible to have super slim binaries. And by default, these are very, very slim. Look at this Hello World program in Rust. Ends up being 288 kilobytes. It's all statically linked, so there's just one linkage to the OS X system, some OS X system library, which is kind of the very basic of it all. And in Go, the program is a little longer here. You get 1.4 megabyte, and without these special LD flags that probably no one knows or uses. Without these, it's 1.8 megabyte, just for default out-of-the-box Hello World program. So you see there are huge differences. The Go binary, by the way, is not linked against anything. It's totally blank. It's kind of their own thing. I don't know how that works, but honestly, I don't know a lot about these kind of low-level things after all. Just as a side note, you can use Rust without a standard library. You can just say, okay, I don't want any of this stuff, I just want the language. And this will further assure that you don't get anything, basically. You have to implement anything yourself, but the program will be as small as it can get. This is something that's useful if you want to program for embedded devices. That is kind of the more detailed part with code examples. Now I prepared a little table for you that kind of skims over all the things that might be interesting to you as a Go programmer. So first of all, indentation, 4 spaces in Rust, 1 tab in Go. That's quite a difference. Personally, I prefer spaces because that will make sure that your code looks the same everywhere. The variables are writable just on demand in Rust, whereas in Go, you don't have a choice. I mean, we don't talk about constants in Go. Why would we? It's not the same thing, but variables are always writable. You cannot specify that something should be read-only. The naming conventions are, well, kind of C or Python-like, right? So it's my type, it's camel case capitalized types, and underscores in function names. Whereas it's kind of the opposite, camel case everywhere for Go. And this is obviously an exported function, so if that as would be lowercase, would be a private one, otherwise it's capitalized. So that's another thing that I personally dislike about Go, because that makes your method calls look wrong to me. And yes, I'm a guy who says, the only thing that may be capitalized is the type itself, and everything else should be lowercase. That's how I think. This is what my brain is wired to. I'm sorry for that, but to me, this caters, this kind of native that looks good in my eyes, whereas this looks wrong and kind of odd. Anyway, my personal opinion expressed here. Please don't burn me for that. The doc comments. I didn't mention that anywhere, but that's a doc comment. So you have the standard comments like in Go, but if you want anything to go into the documentation, you have this style. That is the, package documentation here. And this is documentation for individual items like functions, methods, something like that. And Markdown is fully supported, which means that you can do pretty documentation that will end up pretty in your generated documentation pages. And last but not least, just to say it, you can have doc tests. Yes, you can. Doc tests are just part of the thing, out of the box, nothing to be done here. It's totally awesome. And these doc tests will then turn up in your documentation pages, which will be great for people who want to learn your API, right? So, doc tests, I like them. I thought this would only be possible in Python, but obviously it is possible anywhere. Expressions. Yeah, what is an expression? Expressions in programming languages are things that have a return value. And you wouldn't believe it, but in Rust, everything has a return value. In Go, just some things. I don't know too many there. I think just functions can have return values. But let's focus on this thing. You say, everything? Really everything? Does a for loop have a return value? Yes, it has. It returns the equivalent of void, which is unit in Rust. It returns nothing, basically. But an if clause, for instance, can return something useful. So this allows you to write cool things when initially assigning variables, for instance. But more about that at some other point, not in this talk. Auto dereferencing. Sure, you can borrow things and you can have borrows of borrows. And most programming languages nowadays kind of allow you to auto dereference these borrows or pointers to make it a bit easier to read the code that comes out of there. In Go, everything will be auto dereferenced, but only for one level. That's the thing. So they recently changed this in Go 1.4 because that's how it's part of the specification of the language, one level only. Whereas in Rust, this works recursively, but only when you access members. So if you want to reassign something that is borrowed, for instance, you will still have to manually dereference that with the asterisk there. This operator here, in Rust, you have to think of it as the borrow operator. It's really important to get the ownership tracking idea and the borrow idea into your head. So see it not as an address off operator, which is all it is in Go. Exceptions, interesting topic. Didn't talk about it so much here. Rust will only panic. So if something goes really wrong, you will panic, which will unwind your stack and end up killing your task. The task is the thread that you're running on right now. So if you just have a main thread with your main program, then your program basically dies with a panic and a potential backtrace. Individual threads can still panic without bringing down your entire program, obviously, but there's no way to recover. So you cannot catch anything. If something goes wrong, it goes wrong for real. Your main program can still recover from that, of course, and kind of spawn new threads if you like. But, there's no recovering inside of something that is being unwound. Threading model. In Rust, it's just native threads, so no highly efficient small Go routines that we have in Go. In the end, they will run on actual threads, but Go kind of allows you to spawn like 30,000 of these without breaking into sweat, which can be interesting for web service. For each connection, you have a Go routine, which will be dispatched efficiently on the available threads. Whereas in Rust, you probably wouldn't want to dispatch 30,000 native threads. But Rust has a thread pool for this, so a thread pool just takes tasks and then schedules these onto the threads that it has. So in a way, it's the same thing if you like, but there's no syntactic sugar for it. This is that. So now we are done with the entire 15-minute presentation. I hope it ends up 15 minutes. I have no clock here, unfortunately. I think if I had to summarize this, which I obviously have now as indicated by this big text on my screen, then I can say that Rust certainly is a totally different language from Go. It's a modern language, it's new, it's backed by the Mozilla Corporation, by the way, so in case you thought this is kind of a two-man project, no, it's not. It's a huge community, and it brings to the table something that hasn't been there yet. Making your program safe and fast is totally awesome, and that's something I want. Safe, efficient, and fast. Go can't really deliver that, just because you can't even declare things to be constant or not to be changed. Go keeps it simple. That's also kind of the main difference. Rust has a steep learning curve, I tell you that. So what I've just shown you with the compiler messages that you will get for doing things that you've done previously without issues, you will see these a lot initially. And the documentation that is out there is decent. Everything I've read was good, but it doesn't tell you the whole story sometimes, and you will run into a lot of things that are difficult to understand at first. The compiler is awesome. It's terrific. It's like a person talking to you sometimes, and it's just me, in that case, being too stupid to understand what it actually tries to tell me, even though if you think about it, it's exactly and to the point what the problem was. But as you still have to figure out what lifetimes are and what this ownership stuff really means, which relates to lifetimes strongly, you kind of have trouble to understand sometimes. But that's the learning curve I'm talking about. So Go basically is super easy to learn. I can't remember any trouble I had when learning Go and writing programs in it. But also it's really easy to, have messy programs, whereas in Rust, this is super difficult to do. Also, Rust is faster. All the tests I've done indicate that Rust is faster than Go. Except for the SHA-1 performance, where Go is faster. For some reason, I don't know. But anything else, Rust was significantly faster and very close to C++ performance, which Go doesn't always do. I mean, you know, all these tests and benchmarks are kind of a double-edged sword. I know that, but I'm just saying that's my experience, my feeling. Rust is something that, performance-wise, I anytime would prefer over Go. Also, the looks of it is just gorgeous. I might do more tutorials about that show you how the code can look like if you do it idiomatically. So after all, Rust is a programming language that you should watch out for. On 31st of March, it comes out as beta. Please have a look. Do yourself this favor and have a look, consume some YouTube videos about that, and try it yourself. There will definitely be more, because I really, really want you to make sure you understand that something new is out there that can make your day-to-day programming so much nicer and helps you to write better code after all. And that's all what we want. We want to write great code, great programs that run fast and that are easily maintainable. Okay, thanks for watching, and I hope to see you next time.